last lecture.
Right, thank you. So, yesterday we were discussing certain geometric structures on the moduli space of flat connections, specific to flat connections and surfaces. So somehow geometric structures are very sensitive to the dimension of the manifold on which we study the flat connections. And so today I wanted just to mention, if you take a three-manifold, then of course there are specific, other specific geometric structures on the moduli space of flat connection on the three-manifold. And indeed, this object appeared in the previous talk. So if we take a closed three-manifold M, then and we fix, let's say, compact simply connected group G. So then, on the space of connections on M, so well, first of all, since I took simply connected group G, so G bundles are trivial. So I take my trivial G bundle, I study connections there. So there is a function on the space of connections, which is the celebrated Chern-Simons action function, which eats connection one form. And produces a number, so between the correct normalization, 1 over 2 pi, trace integral over M, 1/2 A which dA plus 1/3 A which A. So, right. This formula is naturally inferred from four-dimensional geometry, and one crucial property of three manifolds is that they are all mu coordinate. So if you use a four-manifold inside M, if you wish, and on the four-manifold you can consider the form curvature wedge curvature. So we can extend this to a trivial bundle over a four-manifold, and the integral over the four manifold of boundary M spits out Chern-Simons action. So somehow this is a three-dimensional story which naturally comes out from the second Chern class for four manifolds. So what I wanted to say is that, well, indeed, the well-known property of this is called Chern-Simons action function. So the well-known property is that if you do a H transformation, so of the action, then this changes by a multiple of 2 pi. So changes by, so G is a map from your three-manifold to the group, and so the Chern-Simons action function changes by a certain number. Simons of A. So the number is so it's some vector times trace integral of G minus G H cube over M. And well, this is so this should be viewed as a pullback of the integral Cartan form of the group paired with the fundamental class of M. And this is normalized in such a way that this is 2 pi times an integer. So this is plus 2 pi times something. So the outcome of this story is that although this Chern-Simons action function itself does not descend to the quotient of connections by gauge transformations, its exponential does descend. So exponential of I chain silence, we can put in here the integer. So this gives you a function from connections and then modular base transformations to unit circle. So right, and okay, so I should say yeah, the unit circle. So now, since we started with a closed tree manifold, so the variation of Chern-Simons action is so proportional to the curvature. So if I restrict this to the flat connections, then the variation is 0, and what I get is a locally constant function with values in U1. So this exponential of Chern-Simons action gives me a locally constant function of the moduli space. Moduli space of flat connections. So that doesn't mean that it is globally constant, because there may be different connected components. But well, here it is. So this gives me a class. Alright, so now I wanted to comment on what happens with this story if you have a three-manifold with boundary. So if you have a three-manifold with boundary, so things change because, Chern-Simons action function stops being engaged in violence, so it spits out rather. So even with respect to infinitesimal gauge transformations, so it spits out some boundary term. So this would before going there. So somehow this geometric structures which are included to moduli spaces of flat connections on three manifolds and on surfaces are related. That is what I wanted to show. So, well, indeed, if we take a three manifold with boundary, so a three manifold with boundary, then have a map from the moduli space involved to the moduli space in the boundary. And well, the theorem is that the image of this map is a Lagrangian submanifold downstairs. So we know that this one is equipped with a T-Watt symplectic form, which we discussed yesterday. And the theorem is that the image is Lagrangian. So L curly, so L straight was this line marble downstairs, so L curly will be this Lagrangian submanifold. Right, so inside CBG, Lagrangian. So, well, one name which might be a little bit confusing for this Lagrangian is the evolution relation. So, well, what should be, well, there are two things which can be confusing here, evolution and relation. So, they are both made clear if you think not about a three-manifold with boundary, but about an interval with two endpoints. So, this is the situation of classical mechanics. And so this is somehow a source for the classical mechanics, so maps into some phase space. So the evolution gives you a Lagrangian submanifold, or given by the, in case of non-degenerate mechanics, by a graph of the flow of an Hamiltonian vector field. So you get a Lagrangian in the phase space put at time 0, so we should reverse sign of symplectic form times phase space at time in time out. So in case of non-degenerate classical mechanics, this would be a projectable submanifold, a graph of phase symplectomorphism, which is the flow of an Hamiltonian vector field. In case of degenerate classical mechanics, in, let's say, very many examples, you also get a Lagrangian submanifold. So, and it encodes the value from time in to time out. And the relation is a set theoretic term. So, just a subspace of the product. This is somehow the evolution relation. Well, the word relation really, so you should think that we have, let's say, two boundary products. Okay, so I want to prove the easy case of this theorem. So I will totally forget that I asked G to be compact. I will. So let's look at G equal to R. So then, so the story is to make sense. I have. So upstairs I have Dirac homology for a three manifold. Downstairs I have Dirac homology for its boundary. Maybe the first one. So I have a map from H1 of M to H1 of boundary. So I claim that the image is Lagrangian with respect to the Poincare duality here, which is what the what symplectic structure degenerates to in this case. And this is actually quite easy to see. So one thing which is very cheap is isotropicity of L. So, isotropicity of L, so this is very easy. So if I have, so let me call this map Y as in here. So I have phi of some cycle on M, alpha, and phi of some cycle beta. Okay, and I wanted to pair them using Poincare duality. So this is just an integral over the boundary of M of alpha which beta restricted to M, so to the boundary. So that's what pi does, just restricts for you closed forms to the boundary. Right, but then what I do, I use Stokes' theorem to write this as an integral over the whole M of the differential of this thing. Since both alpha and beta were closed on the free manifold, I get 0. This is the integral over M of the alpha h beta. This is 0. So isotropicity is very cheap, and well, also here it works very cheaply. So Lagrangianity uses just a little bit more. Lagrangianity uses non-degeneracy of Lefschetz duality between absolute and relative, between this homology and homology relative to the boundary. So how does it work? So I have to prove something in this lecture, right? So let me do that. So I want to calculate L curve, the symplectic orthogonal to L inside here. So this is by definition. So what is this? This is a set of classes in H1 of the boundary, such that for any class alpha here in the bulk, the pairing of pi of alpha with A is 0. So let me call it beta, so that we call it beta. So this is this should be 0 for any beta class in the bulk. So actually, yeah, I should write down for the next term of this. So this map is a part of the Lorentz sequence of the pair, homology of the pair, m comma its boundary. So the next term would be H2 of so the relative homology. So let me call this map, and then this Lorentz sequence. So right. So let me calculate this object. So first I should rewrite this expression. So this is okay. So this is an integral over the boundary of beta restricted to the boundary range A. Okay, which can be rewritten using again Stokes' theorem as the integral over the whole m of so differential of beta wedge some extension of A into the bulk. So which and it may be so that A cannot be extended as a closed form in the bulk, which makes the story non-zero. So okay, and of course so dq beta when it hits because beta is closed. So so this is go up to a sign minus integral of m beta wedge d trivial. And okay, so this is exactly so the class of this form is exactly the value of this connecting homomorphism. So this gives me a relative so a two form which is 0 on the boundary because the boundary A was closed, but well this is not 0 inside. So so this expression descends to cohomology. So this is the pairing between the class of beta and connecting homomorphism applies to the class of A. This is Lefschetz pairing between this object and this object. And so, well, the well-known theorem is that Lefschetz duality is non-degenerate. So this means that if I want this to happen for every beta, this expression should be 0. This means that my A should be in kernel of C, of this map C, which means that by exactness of this sequence it should be in the image of pi. So this proves this case. So I proved that I wrote this time. But the point was that this uses something, uses the non-degenerate subtractions duality. Okay. So okay. Now what happens with Chern-Simons action function on So the following is happening. So and the claim is that well, the exponential of Chern-Simons action function in the case with the boundary yields a horizontal section of the pullback of this line bundle we were constructing yesterday. There's this line bundle, well, held possibly to the tensor power k here. So we can pull it back using pi. So pi star of k over the moduli space in the bulk. So in horizontal with respect to the pullback connection, with respect to the pullback connection pi star of k and now which was the connection here. So, well, to make some sense of this plane, so one should look at well, this is some story happening after reduction, and before reduction, so we had a surjective subversion from connections on M to connections on the boundary. So upstairs we had Chern-Simons functional and its variation, or better said, the round derivative, was -1 over pi integral of or trace integral of curvature which delta A plus okay, so let me call this P. So that it is different letters, so somehow this is form. So plus P pullback of the one form alpha which I introduced yesterday, so A which delta A. Properly normalized. So this is the boundary one form which lives here. So let me write this. Okay. So now if I restrict my attention to flat connections, then the first term goes away. And what does I have that the differential of Chern-Simons action restricted to flat connections is all the pullback of some one form of the boundary. So if I formulate it in terms of the exponential Chern-Simons action, then I should write it delta minus ik pullback of alpha. Exponential of the Chern-Simons action is 0. So exponential Chern-Simons action is horizontal with respect to the connection on the trivial U1 bundle with one form given by the pullback of alpha. So from this point, this should be clear, right? Because well, what we do, we pass to the reduction, but on the boundary something non-trivial happens because we are identifying these U1 fibers over trajectories of gauge transformations on the boundary, so they are not identified trivially, they are identified using coordinates of alpha. So, for example, they expect this. Well, I cannot put is here. It yields a horizontal section. So we are doing something on the boundary, some identification using coordinates of alpha. So, right, in particular, one kind of surprising, or I don't know, what's surprising to me, consequence of this result is that the pullback of this line bundle, so the line bundle is non-trivial, but the pullback is trivial because it has a global section. So this is some peculiar geometric implication of this story. Okay, so this was just a brief comment on the how this structures on the moduli spaces for three-dimensional manifold and surfaces talk. So this is the simplest example of this talking. Right? So now, actually, I wanted to switch to well, to a different story, and well, then, given the time at the end, I will return to a generalization of this one to well, a broader class of moduli spaces, the so-called AKZ moduli spaces, given time. So, okay, I'm not sure. Actually, I think I want to say, well, something related to quantum theory, or to at least in some model sense, because this was all about, well, essentially geometric pictures related to classical transcendence theory. So now I wanted to tell some story, which is called volumes of the moduli spaces of flat connections and surfaces, but I wanted to make life cheaper by specifying to G being a finite group. So I will comment on what happens for the Lie group. I will just cite the result, and it is surprisingly similar, although the problem we are solving is different. So G a finite group. So I should finish erasing. This is really a different story. So, and now sigma is again a surface. So the question is about the volume, so I will tell you what do I mean by volume of the moduli space of flat connections on sigma. So this is a specialization to a trivial case of, almost trivial case, of the construction of, in the paper of diagraph in Britain, possibly 91. But specialization to a more trivial case than considered there. So surfaces, trivial group per cycle. So, right. So what do I mean by volume here? So the fancy name is the volume in the groupoid measure, but actually, so this is just a collection of points. So for G, a finite group. But I want to weight these points with some weights. So what I mean here is, well, recall that this is the space of homes from, well, actually for the beginning of the story, sigma can be of any dimension, but then I want to specialize the surfaces. So, so those would be homes from pi1 of sigma to G, modulo conjugation by G. And I want this number to be just the number for homomorphisms. Number of homomorphisms divided by the size of the order of the group. So this can be seen as, well, sum over points of this set. I call them, let's say, row is also G, where I weight every point with 1 over the size of the stabilizer in the group, or stabilizer of this section. So this is stabilizer subgroup in G. So these numbers these numbers form a very simple example of Atiyah's topological quantum field theory. And well, essentially this means that these numbers associated to closed manifolds, so you can consistently prescribe also something to manifolds with boundary in such a way that you can glue these answers for closed manifolds from the answers for manifolds for pieces if you cast a manifold. So I will not recall for you in full detail TS axioms. This is, I presume that most of you know. So in this case, I'm supposed to prescribe some vector space to a closed n-1 dimensional manifold. I should associate some space of states. So I should construct some space of states, and I should so for an n manifold and with boundary. So with boundary, so I should construct the partition function z of m, which should be a vector in the space associated with boundary. I construct some vector. And well, the main feature, so there is a set of axioms this is supposed to satisfy. So if you take disjoint unions assent to tensor products for vector space, and also for the partition functions. But probably the most important axiom is the gluing axiom, which says that, well, okay, so those are supposed to be Hilbert spaces, and actually the TS setting can be simplified for this case, because this is somehow TQFT not sensible to orientations. So these can be viewed as being over reals or over rationals. So they would be just Euclidean spaces, so with some inner product. So it's not necessary to make them complex vector spaces with Hilbert inner product. So the main gluing axiom tells you that if you have, let's say, a manifold M with a boundary which is split into 3 pieces, we call it B1, B2, and B3, and I want so B1 and B2 are diffeomorphic, and I can glue them to form a new manifold M2 by gluing. So I identify B1 with B2. So the gluing axiom tells you that the partition function for M2 should be constructed from this one by just, okay, so how does it work? So partition function for M sits inside H B1 tensor H B2 tensor H B3. And partition function for M2 sits inside H B3. And so the map here is just a pairing of these first 2 spaces using this structure and gradient. So in this case, in the case of counting homomorphisms from pi1 to the group, so what is this data? What are the spaces of states and what are the partition functions? So it is as follows. So the space of states for me would be just the span over my chosen ground field, so maybe rationals or yields, say yields, of just this collection of points, which is more or less space of flat connections on B. This B is an n-1 dimensional manifold. And partition function for a manifold with boundary, it should be some vector, so it is given as follows. So it is so it is 1 over the number of elements in G, sum over over the classes, so points of the moduli space for the boundary. Right. So here I should put well some number, which is the number of maps from phi 1 to G, which homomorphisms, group homomorphisms, which induce a particular conjugacy class of homomorphisms on the boundary. So the given class. Oh, so I am doing something terrible. So let's see. So this will be beta. Okay, this will be beta. Okay, this will be beta. Well, times this basis vector associated to beta. So I'm putting this in square brackets because I'm thinking of this as being class of homomorphisms modular conjugation. Okay, so well, one important thing that I did not tell you yet is what is the inner product of this space upstairs. And while the doing exam will work only if I choose a particular inner product. So this is actually in this space for B equal to the boundary of M. And right, so what I should tell you is that the inner product upstairs is the following. So inner product of alpha and beta is the size of the stabilizer of alpha, stabilizer subgroup. So I view alpha as in beta as being homomorphisms from pi 1 of B to the group, and on this homomorphisms G acts by conjugation. So I can ask about the stabilizer subgroup. So if alpha, the class of alpha equals the class of beta under conjugation, and 0 otherwise. So this is somehow this basis is orthogonal but not normalized. Okay, and it is, well, I would not like to go into detail why this choice makes the Green axiom work, but it is rather easy if you think about that, but well, you should think about that. Essentially, the point is that when you group two manifolds, you divide by conjugation on the boundary 2 times for the 2 pieces, and you want to compare it to the answer for the single manifold where you divide only 1 time. Well, this is a very vague explanation, but it is an exercise to make sense of it. So, okay, so we will see in some simple example that this prescription works. Okay. So now let me specialize to the case of surfaces. So let me specialize to the case of surfaces, so I have to raise this in restrictive size. So in the case of a surface, so n equals sigma, surface continuous h, Sorry. So, if we are considering the full TPFT, we should consider surfaces with boundaries. So, boundary is a collection of circles. So, and according to this formula which I just raised, the space of states for a circle should be the span. The vector space whose basis is associated to points of to conjugacy classes of T, which is a finite set. And the inner point of two conjugacy classes is the size of the stabilizer in G or 0, depending on whether the conjugacy classes coincide. So now a surface, a closed surface, can be, as is well known, can be cut into, let's say, disks and pairs of pens. So there are many ways to do that. For instance, like that. So in this picture, so there are, so G is G, so I get 2H pairs of pens. So this is, let's say, 1, 2, 3, and so on. 2H pairs of pens. So 2 from each hole. Pairs of pens. And 2 disks. Well, with this choice, there are lots of other choices. 2 disks. So I would like to know partition functions for disks and for pairs of pens. So, okay. So for a disk, I get, but by definition, which was there for a race, I get 1 over G times, well, just this vector associated to the unit conjugacy class. And so in particular, so we can check that we get a consistent answer for S2 sphere. So on one hand side, from the definition, it should be 1 over G, because there's the fundamental group is G, and well, the sum that was there just gave me 1. So I mean, in the numerator, there should be the number of homomorphisms, and it is 1. So and on that hand, it can be computed from gluing epsilon by gluing 2 disks together into a sphere. So this would be 1 over G times 1. So those are these 1 over G's times squaring of 1 with 1. And here I give my prescription. So this would be the size of the stabilizer, which is the size of G. So this is indeed an equality, and one needs to see that prescription works in this case. So now if I take a pair of pens, then the partition function by definition is sum over 1 over G, sum over triples of root elements which multiply to 1. So that ABC equals 1. So that's the product of these 3 vectors associated to A classes of A, B, and C. Okay. So now, okay, and this this corresponds to this presentation of fundamental group of the pair of pens with these generators. So this should be, well, this whole should be A, B, and C. Okay, so now the way to actually calculate the answer is to do something like a Fourier transform, to find to change to another basis in this space of states. And well, there is a basis which is much nicer for equations than the one associated to conjugacy classes, and this is the basis of characters. So the point is that, well, each dual for a circle has another dimensional basis, the basis of characters. So the basis of characters of reducible representations. So characters, well, let me note the representation Ri. So character Ri shifts from the set of quantity classes to complex numbers. And so I would like to introduce all these basis vectors in the dual space and to define their pairings with vectors associated to quantity classes. To give, so these numbers should be values of characters. I can pick a representative. So this defines for me how to pass from one basis to another. So I can, using the inner product structure, I can transfer this into a basis in H itself. So I can use the inner product to construct a basis in H. Okay, so so what I get is the following. So rules for going from one basis to another. So this can be inverted using Schul's orthogonality relations for characters. So I can reverse this expression. So this is sum of quantity classes. One over the sign of stabilizer character of A inverse vector associated to A. Okay. And now this basis is orthonormal. So, and then what is nice about this basis is that, well, you can rewrite the answers for the disk and for the pair of pens, and so what you get is the following. So, the partition function for a disk becomes 1 over G sum over irreducible representations, dimension of the representation times the vector. So, well, all right. But the curious thing happens with the answer for the pair of pens. So in general, well, this belongs to the tensor cube of space of states. So you expect all sorts of triple tensor products to appear. But the miracle is that in this basis, only diagonal products appear. So the answer. So all these expressions follow from previous ones using Schul's orthogonality relations, which allow you to calculate things. So the answer here is sum over representations. So you only have diagonal products with some coefficients. So now, if I want to calculate, so using this data, I can calculate everything. For instance, I can calculate the partition function, the number, the partition function for a closed surface. And well, I should sum over colorings of every circle I pass this surface by basis elements, basis vectors of the space of states. But in this basis, I only get an interior answer if I color every surface with the same representation R. Right? Otherwise, well, it would give me zero contribution to the partition function according to this formula. have to cover every circle by R. So the answer the grooming axiom gives me from this data for the partition function is, so the partition function of this is well, sum of representations of say order of G divided by the dimension of the representation to the power number of pairs of lengths minus the number of digits. And this is well to h minus 2, or you can calculate it as minus the order characteristic of the surface. This is 2h minus 2. So this is the answer for this volume of the moduli space of flat connections on surface. And well, so the beautiful thing about it is that it is expressed in terms of well, sums of over reducible representations of dimensions of these representations to some power, which is minus the order plus the order characteristic. So this is the answer for this simple problem, which comes from the fact that you can promote these volumes to an adheres to PFT. So now a more difficult problem to which I will only cite an answer is to do the same in the case of a Lie group. So if I have a Lie group G, then the volume has a different meaning. So the meaning of the volume is a symplectic volume. I have a symplectic structure. I can take its top. I can construct a volume form out of it, and I can integrate it. And the question is, what is the answer? And the answer is surprisingly almost the same. Is well, the expression in terms of representation of the group. So, so symplectic volume. In case of sigma still a surface and G a Lie group. So here the question is, what is the integral over a moduli space of the, so I take a clear symplectic structure to the, well, the maximum possible non-trivial power. So it's H power. So over the factorial of this number. So this is the symplectic volume by definition. So I can normalize omega to be an integral class. So this is by construction a rational number. So this number was well, one reference is the work. So let me see. So it is a paper by Newton called on quantum gauge theories in 2 dimensions. So this number has appears in 2-dimensional Young mills and well in its topological degeneration of the 2-dimensional BF theory, and is, as I will tell you in a moment, it also has a direct connection to the quantum Chern-Simons theory. So this number is the answer. So in case when the genus is 2 or higher, is the order of the stabilizer of the group. So for okay, some factor which I don't really care so much about. And then the part which
I think you meant the order of the center.
Sorry?
You probably meant the center when you said stabilizer. Z
Yes,
is
yeah.
the center.
Yes, I said stabilizer, sorry. Yeah, center. Right. Sorry. So, and here, something we should recognize, sum over representations, 1 over dimension representation to the power 2h minus 2. So, in case of the Lie group, this is indeed an infinite dimensional, an infinite series. So, which, by the way, converges. But okay, before we had just a finite sum over finitely many reducible representations of a finite group. Here we have a sum over reducible representations of a Lie group. But the summand is the same. So somehow, this is, I don't know, it may look very surprising, but somehow the inherent technique to produce this answer is very similar. So you also find some answer for a pair of pens, which also diagonalizes in the appropriate basis. And so somehow the answers look the same because the technique which leads to them is very similar. Although the question we asked was stated in different terms. So now just, so I have like 2 minutes, 3 minutes. So I should comment probably on the relation of this answer to 3-dimensional Chern-Simons theory. So the relation is as follows. So 3-dimensional Chern-Simons theory is an Attias TQFT. So there is a space of states you can associate to a surface. So this space of states is the Linde space, for instance. So can be so for Chern-Simons at level k. So it can be described, for instance, as so hope I'm not cheating. So this is the moduli space of flat connections for the surface. So and this is the line bundle we were discussing yesterday. So the space of homomorphic sections of this line bundle, so I can infer homomorphic structure, a homomorphic complex structure from this marginalized reduction construction. So it is easy to construct a complex structure on the space of all connections, given a complex structure on the surface. So actually, there is a family of these objects parameterized by complex structures on the surface. So the point is that this is a finite dimensional vector space, given that G is a complex group. Here it is very important. So a finite dimensional vector space with lots of structure, projective action of the macroplasm, and so on. Well, one kind of first property of the vector space is its dimension. So the dimension is given by the formula. So so it can be written as a number of ways to color. Okay, let me write. I can write the formula which looks more mysterious than the one which looks less mysterious. So if you look at this formula, it's totally unclear why this is an integer. But okay, it is an integer. So the other property is that if h is 2 or bigger, this is a polynomial in k of degree. Sorry, I'm very sorry. This is a specialized result for the Lucas sequence. I'm sorry to say that. So this is a polynomial in k of degree 3h minus 3, I believe. Okay, and the point is that this number gives you the leading term, leading coefficient of this polynomial. And this is actually making sound very surprising, but there is a reason to that, and this is because this number can be calculated using a Riemann-Roch Hirzebruch formula. So let me just finish with this. So the dimension of this voltage 0 and 1. Well, by certain miracle which has roots in algebraic geometry, the higher homology groups here are 0. So this is actually the other characteristic of this complex. And this can be expressed by Riemann-Roch-Hirzebruch formula as the integral over m plus the class of the tangent bundle to m times the exponential of k times that Riemann symplectic form. And the point is that this is something starting from 1 plus higher forms. So the right hand side is obvious. So is obviously polynomial. So this does not depend on k. It's obviously polynomial, and the leading term is obvious from this formula. This one. So this gives you a direct comparison. So the leading coefficient of this object related to three-dimensional transcendence theory is something related to two-dimensional Dampings or BF theory. So I'm sorry I ran out of time. I didn't tell you anything about AKC moduli spaces. So you can ask me if you're interested. But then it's over. Thanks very much.
What did you want to say about AKs and modular space?
No, I just wanted to introduce them to somehow show that there is a family of moduli spaces where the parameter is not the group but rather this supermanifold with certain structure, and these moduli spaces have very similar structure to the one which I was introducing to in the case of Chern-Simons. So that if you have a manifold with a boundary, for instance, you will have a Poisson or great Poisson structure from some moduli space from the bulk, and the symplectic structure of the moduli space from the boundary.
Can you define those modular spaces really, since you don't know the finite H transformations?
So you are only defining them as integrals, as leaf spaces of some distribution, so you forget about finite H transformations. So those are not honestly, they don't capture all the structure.
Any more questions? No? Okay. We can.